Okay. Thank you, Athanase. Okay, so thank you for coming back. And so today I'd like to talk about tangent spaces and cotangent spaces of dimensional space equipped with norm induced by the Thurston metric. So then on the first, in the first lecture, I talked about geodesics and with respect to this Thurston metric, but I haven't touched upon infinitesimal structure of this matrix. Although I said that it's a feature structure, so that norm induces a distance, but still I didn't talk about this norm and how this norm look like or something like that. So today I'd like to focus on tangent space and the cotangent spaces of Teichmüller space with respect to this norm. So let me recall you that for a tangent vector in the Teichmüller space V, so its norm, the Thurston norm, or as I said, it's not good to call it Thurston norm, but the norm with respect to the Thurston metric is has an expression like this. So it's a supremum of the DLCV divided by the length of C with respect to X. So V X. Oh yeah, X is here. Okay, and take supremum by the making the C range over the set of the simple closed curves. And the length X of the C was the geodesic length with respect to the hyperbolic structure corresponding to this point X. Okay. And so this was the norm. So this tangent space is a norm space with respect to this norm. And as I said, because it is smooth. Yeah. At least it's differentiable. So I don't know if it's smooth in the sense that it's in C infinity, but it's at least differentiable. And okay, and that's the definition of. And as I said, that Thurston distance, Thurston metric is asymmetric. So the norm doesn't have also the symmetry. So the minus of V may not be equal to so the norm of the minus of V may not be equal to the norm of V. So that we should always put it in our mind. Yep. Variation of the norm, right? Yeah, that's right. And so we also like to consider the cotangent space of the D. So it's the dual of this space, this tangent space. So you have a dual norm. So for B asterisk in Tx. So we have a dual norm. Okay. It's a dual norm in ordinary sense. That means it's just a supremum of the vector whose norm is 1. So probably it's better to change the symbol here. And okay. That's a dual norm, okay, in our ordinary sense. Okay, so we have again another norm space, which is a cotangent space of the Teichmüller space with respect to this norm, dual norm. So today I'd like to show you how they look like, or the unit sphere of the norm look like. So let me just remind you of this fact. So if you have a Riemannian structure on a manifold, so you can consider of course, the inner product. By definition, it has an inner product on the tangent space. So that also you can consider norm, and you can consider the unit ball or unit sphere with respect to that norm, and then. Where? Dual norm. That's W. So this is the dual. So that you can evaluate it by V. So that's not U. That's the W. W star. Okay. And so what am I saying? So if you have a Riemannian structure, then you have an inner product on a tangent space. So then naturally there is a group preserving this inner product. That's an orthogonal group. And the orthogonal group should act on the tangent space as a linear isometry. So that means the unit sphere must look like real sphere. So that's a Riemannian case. But in Finch-Lie case, there's no inner product defined on a tangent space. So the shape of the unit sphere might be quite different from this kind of real sphere. So it may look like, so because we don't have a symmetry, so it may look like this, for instance. That's possible. So that's why we have to study the convex structure. So if you have a sphere, there's nothing to study. Yeah, sphere is sphere, that's all. But if you have such a kind of symmetry, you can talk about it for example, how many faces do you have? Or how many, so how it looks like. There might be a part which look like some kind of the round arc. But so if you have such a kind of thing, then you can count the number of the faces or where the faces are, or where is this kind of the round part lies or something like that. So there are many things to study. So this is the situation for the Thurston metric. Okay. That's why it's important to study this unit sphere with respect to this norm, the convex structure of the unit sphere. Okay. So now I would like to deal with the tangent space first, and then we'll move on to the cotangent space. So first, the S of X is defined to be the unit sphere in a tangent space. And Sx asterisk is defined to be the unit sphere in a cotangent space. Equals 1. Okay, sorry. Thank you. Okay. Yep. Yes, yeah, exactly. I will talk about it later. And so we start with this one. So let me remind you that there is of the fact that there is geodesic ray, which is a stretching ray. So that lambda was a maximal geodesic lamination on S with respect to this hyperbolic metric X. And lambda, so this was defined to be a so defined on R plus to dx. Okay. And so we would like to consider the derivative of this ray at the point at the origin. So that's something like this. And I will write it as lambda x. So we call it the stretch vector. So it's a tangent vector of the stretching ray at the origin. Okay. Right? Because the speed of the stretching ray is exactly 1, so that this has a norm 1. Okay. So from now on, we drop this x because we are always staying in a tangent space of x, and so we just write like bold v sub lambda for this stretching vector. And what we have to, so this is a fact that the unit sphere has flats. So that means a part which is flat. So that it is something like a face. So there is a part which is like this. So we can show that by just looking at the stretch path, stretch vector, sorry. So suppose you have two maximal geodesic laminations, lambda 1 and lambda 2, and assume that they share which share sublamination, which is chain recurrent. So the chain recurrent sublamination mu. So mu is contained in the intersection of these two. And then we can show this thing. If you consider the norm of this one. So usually, so because it is a norm, if you consider such a thing, the norm of this one is less than or equal to 1. Okay? But in this situation, you have mu lying in the intersection of these two. And if you consider how mu is stretched by this vector, then that should be 1. So that means, because we are considering the Thurston norm is something like this. So if you consider this one, and C tends to mu, then you can see the supremum should be 1. So that means this has norm 1. Okay, or T in this interval. That means, so if you have these two stretch vectors, B lambda 1, B lambda 2, and you consider the linear combination of these, so or a segment between them, then all of these vectors lies on the unit sphere. Okay. So that means this Sx has some flat part. It's not round like this. Okay. So in a theorem, which I will show you later, so we will exactly determine what kind of the form this has, or the face we describe exactly what are the faces of this unit sphere. But this suggests that there is some flat part in the unit sphere. Okay. And now we turn to the cotangent. So space, which is, so this is a unit sphere in the cotangent space. And for this, there is a good proposition proved by Thurston. So we consider something called a major delamination. So I haven't defined a major delamination yet. So major delamination is a geodesic lamination plus transverse measure. Transverse measure. So by transverse measure, we mean something like that. So if you have a transverse arc, so such a thing which is transverse to the leaves of the geodesic lamination, then you get some number, some positive number. So it's a measure defined on the transverse arcs. And the property you should have is if you just move it parallelly to the leaves, then the value doesn't change. So it's a measure defined on the transverse arcs and which is invariant under the parallel translation along the leaves. So that's a transverse measure. So if you have a transverse measure on geodesic lamination, it's called a major lamination. But we always assume that the support of the measure, so transverse geodesic lamination, is equal to the entire lambda. So transverse lamination should be, well, this might not be good to use mu here. Probably m is, have I already used m? No. Okay. So this should be m. So this means the support of the measure is the entire lamination. So I mean, if you have such a thing, for instance, leaves spiraling around the closed geodesic, if you put a measure here, something like a Dirac measure, for instance, then that should diverge as it approaches this closed geodesic. So you cannot have a measure here. So this cannot be a support of the transverse measure. So this cannot happen for a major lamination. So I say that the general geodesic lamination may not be the support of a transverse measure. So, but on the contrary, if you have a disjoint union closed geodesics like this, then it has a transverse measure. You can just put a Dirac measure for each component, then you get the transverse measure whose support is exactly this disjoint union of closed geodesics. Okay, it's clear? Any questions? All right, so we consider the space of the major laminations on there. On this, to be more precise, that should be S with a hyperbolic metric. So it's just a set, but you can put a topology there. So because we have a transverse measure, we have a weak topology with respect to this measure. So that means if the measure for any arc is very close, then they are close in this space. And that was first introduced by Thurston, and he also showed that it's actually homeomorphic to Teichmüller space, that the Euclidean space of the dimension 6G minus 6 plus to C. Okay. And we also would like to define a projective version of this space. So that this is a projective space with respect to that. That means we consider this space. This contains also the empty set. The empty set is also regarded as a point here. So it's and take away the empty set and divide it by the scalar product. So that you can, if you have a non-negative real number, then you can multiply the measure by this number. So that's the action of this Laplace on this space, and you can consider the quotient space with respect to this action. Then you get this is called a projective lamination space. So because this is kind of origin, and so if you take it away and then consider the quotient, then that should be the homomorphic to the sphere of the dimension 1 less than this. Okay. And there is an important fact proved by Thurston. So in this space, so you can, so for a simple closed curve or a simple closed geodesic, you can put a Dirac measure, and any Dirac measure, if you have a two transverse measure on defined on a simple closed curve, then one is just a scalar multiple of the other. Therefore, that this in a projective lamination space, that each closed geodesic is just one point. And so this set of the simple closed geodesic can be regarded as a subset of the PLS. And the fact is that C is dense. Okay. So in other words, so for any measured lamination, there exists a sequence of simple closed curve and a weight such that this weighted simple closed curve converges to lambda. Okay. Any questions? Okay. Yep. C is the set of the simple closed curves. So this is the set of. Sorry, this one. Okay, so this is the number of cusps. Yeah. So we are considering the finite type orientable surface. So that you may have a cusps, so there's a number of cusps. Now we can define the map from the product of the measured lamination space and the Teichmüller space. It's a function defined on this product. So for lamination and point, so the image should be the length of this measured lamination with respect to x. So what's the length of the measured lamination? So the one way to understand it is to just consider this kind of sequence. So you have a length for the simple closed geodesics And if you have a weight there, then just put that weight as a multiplier of the length and take the limit. Then it turns out that it converges to some number and it doesn't depend on the choice of the sequence. And that's the length. So the other way to understand it is so you have a measure here. So this is so something like this. So this is the measure. So this is infinitesimal version of the measure, and this is a length element along the leaves. So you have a length element here, and then you have a measure here, and then you consider the product and take the integration over the entire surface. That's also another definition. Okay. Now, so we can regard this function as a function defined on the MLS from MLS to the space of the function from TS to from TS. This is actually infinity, but they just put it as a C1. Okay. So if you fix one, then you get the function like that. So for each lambda, you have a function like that. So you can regard it as this. And so this is just if you for fixed lambda, you get the function like this. So this is just the length function. This is something like this. So so if you for each lambda you have a function like that. So that function is denoted by that. So this is the image of. So this lambda is sent to L lambda here. Okay. So it's a length function. So you fix lambda. Then for each point, you have each point in the Teichmüller space, you can define the length of the lambda with respect to that point. So that's L lambda. Okay, so because of the differentiability, so you can consider the differential or derivative of this function at x. Okay. So this is the function from the Ts to R, because this is the function like that. And of course, because it's a differential, it's a linear. So this is an element in the cotangent space. Okay. So this defines a function from, well, there's no space there. So let me return to this starting point. So this d L lambda x is contained in cotangent space. So so if you make vary lambda, then so here lambda, then it defines a function from MLS to a cotangent space. Okay. So I like to have okay. Right. And if you consider instead of this, so if you consider something like d log L lambda, then this is d L lambda divided by the L lambda x. Okay. And this is nothing but the length of the lambda at x. Okay. And if lambda, and if you consider two measured lamination, the one is lambda and the other is lambda prime, and if one is probably what was a good symbol here? I also run out the symbol. Anyway, if one is scalar multiple of the other, something like k, okay, then the log lambda prime, d log L lambda prime is equal to the dl lambda prime and x, and so both of them are multiplied by k, so it's the same as sorry, there's no prime here. So that means, so if you take a log, then the image here depends only on the projective class of the measured lamination. So that means if you consider log L, something like that, then you can define a map from the projective lamination space to the cotangent space. Okay. And now, at last, I can show you this proposition by Thurston. He showed that actually this is an embedding of a PLS to a unit sphere. So d log L embeds PLS to the unit sphere onto unit sphere of the unit sphere. That means Sx. Okay. All right. Oh, sorry. Why I reversed? So that the log embeds PLS onto now. This fact implies the existence of the flat part in the cotangent space. So suppose you consider measured lamination lambda, and suppose the dimension of the transverse measure, the space of the transverse measures on lambda is greater than 1. So a typical example is something like this. So if you consider the lamination like this, then you can put the Dirac measure here and there independently. So you have a two-dimensional space of the transverse measures here. So it's a typical situation like that. But the other situation, like so even if the lamination is something like exceptionally minimal, then there's a possibility that the measure is not uniquely ergodic, then you have such a situation also in that case. So anyway, so then this space, so probably okay, what's the good symbol? Probably W. Then the image, so W so if you descend to the projective lamination, so it should be W bar, it still had dimension, positive dimension. So the image of this one has a positive dimension. And it's because it's linear, and this is a linear part in the projective lamination space. So you can add these two measures. So for two measures here, M1, M2, we can consider Tm1 plus 1 minus Tm2. If they are linearly independent, so you can consider something like that. And it constitutes a linear part in W bar, and it's mapped to a linear part in the unit sphere. Yep. W is the space of the transverse measures on lambda. So in this case, it's you have two non-negative real numbers. So that's W. W bar is its image in the projective space. So now we could show that in both in tangent space and cotangent space, we have some linear parts. Okay, so it's not round like in a Riemannian metric case. So now, so here are some terms in the convex geometry. So this seems to be a general terms used in the convex geometry. So we define especially two notions. So suppose you have a convex body. So this is a very general situation. So just forget the Teichmüller space for now, and consider some convex body B in the Euclidean space. Probably it's better to assume that the origin is contained in B. But anyway, so its boundary is a sphere, and sometimes it's called a convex sphere. So in our case, the Sx, script Sx or the script S star x are the example of such things. Probably it's better not to use S because I denote the surface by S, so probably sigma is better symbol. Okay. And so here's the definition. So the subset of sigma F is defined or said to be a face of S if first the F is convex. That's the first condition. The second condition is that for any segment YZ, here Y and Z are contained in S, intersecting F, these endpoints should be also contained in F. So the first is the convexity, and the second is some kind of the maximality preserving the convexity. So let me draw a picture to explain this. So you have something like this kind of form, okay, right? And so this is not face. oh, sorry, this intersecting F at its interior. This is, at the interior means the some point, not the end point of the segment. So this is not the face, because this is convex, but this is not the face. Because you can consider something like this, intersecting the red one at middle, but neither y nor z lies on F. But, sorry, it's a sigma. So, but this one, this is a face. Why? Because if you try to, you put the 2 points so that it rises, both of them rise on the sphere, and this convex sphere, and try to make it intersect this is not the orange one, and at the middle, then the end point should be also contained in this orange line. So this is a face. This is not face. Okay. Right. But I should remark that if you have a round part like this, for instance, suppose this is a complex sphere, then for such a point, this is also face. But the point lying middle of this segment, this is not face. But this point, this is again a face. So here I wrote something. This is face. Okay, is it clear? And another definition. So suppose, so yeah, I already used F, so E would be. So a subset of sigma, which I denote by E, is said to be an exposed face if E is an intersection of sigma with hyperplane, something called what's a good hyperplane. Hyperplane means codimension 1 affine subspace of Rn, which separate the Rn into 2 parts, and B is contained only in one component of this. So if E is the intersection of such hyperplane is S, then it's called an exposed face. So it's easy to see that exposed face is always face. But face may not be exposed face. Okay. Example is a point like this. So the for instance, a point like this. This point. This is a face, okay? by definition. Well, you can check that it's a phase easily by checking the definition. But this is not exposed. If you try to consider, in this case, the one-dimensional affine space containing that, then it should contain the entire line here. Now, if you change if you perturb this to this direction, then the touching point changes. So it never appears as an intersection of the these two. So it's not exposed. Yep.
Just to clarify what the space is, so it's according to your definition, any convex subset of the face will also be a face?
No. So if you have this, and this is a face, for instance. So this triangle is a face. But this segment is not a face.
So what part of your definition?
If you consider y, z like that, so this intersects that, but neither y nor z is contained in this area. So it's not a face.
Oh, okay.
Yeah. Oh, sorry. Again, I erased the wrong part. So exposed face is a face, but the face may not be exposed. Okay? For face, okay, so not exposed. Right. Right? Yep. Right? It's a face, but not exposed. So this is an example. Okay. It's not exposed. It's experiment. No, not necessary. If you consider the product of this one, is this. So this is not exposed, but it's a face. Product of this one is an interval. So now, at last, I can show you some results. So, first I will tell you the two theorems, and it's a collaboration with Bernardin and Athanase. So here's the first theorem. So any face of Sx is expressed in this way. With some chain recurrent lamination mu. So here's a definition of F mu. So we consider something like K, P lambda K, such that all of them are maximal chain recurrent laminations containing mu. So K can also vary, and these are the stretch vectors. So what you fix is just mu. So consider all maximal chain recurrent laminations containing mu and form this space. So these are the scalars. Okay. And the other direction is also true, that f mu is always phase. So every phase has this form, and the space with this form is always a phase. So it's a characterization of a phase of the SX. Okay? The second theorem is like this. So that this phase F mu is exposed if and only if mu is the support of a measured lamination. So this is the characterization of the exposed phases. So for instance, you can think of the disjoint union of a simple chord geodesics like that. This is, so you can put the measure, Dirac measures here. So that it's a support of some measured lamination. So if mu is something like that, then F mu is exposed. So this is exposed. On the other hand, if you consider the lamination like this, this is as I explained last time, this is a chain recurrent lamination. But there's no transverse measure supported on this. So if mu is something like that, that is not exposed. So that means we know that there are such flat parts, but this theorem, the second theorem, says that there are also round parts. If everything is flat like this, it's like in a polyhedron or the polytope, then everything should be exposed. Every face should be exposed. But the second theorem says there are non-exposed faces. So that means there are also round parts like this. Okay. And probably there's a third theorem. So a point in a face is an extreme point. Extreme point means that there's no segment containing it at the interior, which is contained in that face. So this is an extreme point if and only if V is a stretch vector along a maximal chain recurrent geodesic lamination. So let me just say that so for such a face, suppose this is a face. This is extreme point. These two are extreme point, and these points are not extreme point. Okay. So it's something like a vertex. It's a generalization of the vertex. So here's another remark that the stretch vector may not be extreme point in general. So if lambda is not, lambda is maximal, but not chain recurrent, then V lambda is not an extreme point. Actually, what we can show this. So if you consider something like this, so this is chain recurrent, and this is also chain recurrent. So these two are, this should be lambda 1, lambda, probably lambda plus, lambda minus, and we consider something like this. This is lambda, probably not. This is plus, oh, sorry, this is plus, this is minus, this is not. Then we can see that lambda naught is a linear combination of these two. Oh, sorry, this is stretch vector. We can prove this by calculation, actually. The direction is opposite. So this is spiral like this. This is spiral like this. Okay. So this one is not exposed because it's the midpoint of the two extreme points. The segment connecting the two extreme points. Okay. So these three theorems, some kind of the describe how the convex structure of the unit sphere look like. Okay. Any questions up to here? Yeah, I will talk about cotangent space next after this. Okay. Now I turn to cotangent space. So recall that there is an embedding, so this is cotangent space, Sx star. And recall that there is an embedding of the projective lamination space to the this unit sphere. It's actually the homeomorphic, and so I use the symbol iota x to denote this embedding. Okay, so here is the theorem, the fourth theorem. This is not the work with Ramanujan, but so this is a collaboration with IISER. And Athanase. So any face f of the cotangent unit sphere has the following form. So there is a measured lamination lambda And so probably the phase F star. F star is equal to the, oh, sorry, something depending only on the support of the lambda, which is iota x of mu, such that the support of mu is contained in the support of lambda. And conversely, if you have if you consider such a kind of set, it's always a phase. And the phase is always any phase is exposed in this case. So the situation is quite different between tangent space and cotangent space. So in a tangent space, there are a lot of non-exposed phases. Okay? But in a cotangent space, every phase is exposed. So the shape of the spheres, unit spheres in the tangent space and the cotangent space are quite different. That's a very interesting point. Okay, so I have 15 minutes. Okay, let me just probably tell you how we can prove this. So here sketch of the proofs. This is how to prove the theorem 1. So that we have such a kind of we define such a kind of thing, that f sub mu, which is an expression like that. Okay. And it's easy to see this is actually convex, because by definition, if you have two such things, then it's the linear combination of these two things have the same kind of linear, same kind of form is a linear combination. So that this is very convex. But what we don't know is it's really lies on the unit sphere. So this is convex by definition. But first, you have to show that it really lies on the unit sphere. To see that, you can check that. So usually, as I told you before, that if you have such a kind of combination, because each of the, I forgot to put the important condition that this, to make it on the sphere, that should be, the sum should be equal to 1. Okay. Sorry, that's very important. So we are considering the entire space. So for the sphere, this should be necessary. So because the norm of each one is 1, so if you consider such a thing, in general, the norm is less than or equal to 1. Okay? Because of the triangle inequality. So what we have to show that it has really the norm 1. Okay? To see that, so the point is that this condition. So these laminations, lambda 1 to lambda k, all contain mu as a sublamination. And the mu is assumed to be the chain recurrent. So chain recurrent means it's a Hausdorff limit of the simple closed curves or simple closed geodesics. So if you consider the sequence converging to mu, so in the Hausdorff topology, then because all of these vectors stretch mu by the unit speed infinitesimally, then the stretch on the CI should converge to stretch of mu, and the stretch of mu is equal to 1. So that means this one, the LC1 V divided by length of the CR. Okay. This should converge to 1. So in what that this also so that we call that supremum. This was the definition of the norm, and if you consider sequence Ci like that, then this converges to 1. That means this is greater than or equal to 1. Okay? For the V for this vector, for the vector in mu. Okay. And the other inequality is just a general factor for a norm. So that means the norm of this one is equal to 1. So that means f mu always lies on the unit sphere. Okay. Right. Any questions? And the next step should be to show that it's a phase. But actually, this is the most complicated part, and I don't have enough time to prove that. So let me just stop that proof of the theorem 1 here, and turn to the theorem 2. This is theorem 1, theorem 2. So theorem 2 shows that it's a characterization of exposed faces. So okay, so if lambda, no, not lambda, what's that? Mu, okay. If mu is the support of some measured lamination, then let me use the same symbol to denote the measured lamination. Then you can consider this hyperplane. This should be something like pi mu. Yep. So this is a vector for which the derivative of the length function with respect to this measure lamination mu is equal to 1. Then we can see that actually f star mu is equal to the intersection of the unit sphere with pi mu. Okay. Right. So you have a hyperplane realizing this face as an exposed face. And in 5 minutes or so, let me just show you the proof of the projective, the cotangent space version. Okay, so where is the eraser? Oh, there. So here we are considering something f star lambda. And so by definition, this is convex because you have the addition of the measures and the DL is a linear map, so it's convex. And so what we have to show is that it's an intersection of the unit sphere with some hyperplane. So for that, take some maximal chain recurrent lamination nu containing this support of lambda. So that the complement, so the newly added leaves are all spiraling around or around each leaf of the complement is a spiral around lambda or tends to a cusp. So you have lambda here, but if you'd like to add leaves, that should be something like this. So going there, you cannot put the new leaf here, for instance. The end of these leaves are always spiral around the original lambda. That's how to choose new. Then we can show that this f star lambda, which contains iota x of lambda, is expressed as an intersection of this one with a hyperplane pi nu. And the pi nu is defined to be the cotangent vector such that the value of the stretch vector along nu is equal to 1. So if you take any point in the unit sphere in a cotangent space, it should be expressed like that. And you have a face like that containing that, and it's always exposed. So that means every point lies on an exposed face. Okay. And every face is exposed. So that's a picture of the cotangent space. It is quite different from the case of the tangent space. Okay, let me stop here. Thank you very much. So there will be another talk on Monday. Completeness of the feature, yeah, that's complete, yeah. We know that norm, the norm is always, so what do you mean by complete? Or the distance, you mean, the metric. Yeah, the metric is complete, yeah. Yeah. Yeah, but we can consider the forward Cauchy sequence and the forward completeness or something like that. Yeah, so actually there's something like that, the forward completeness. So it's a forward complete. So because you cannot change the order of the two, so we consider the Cauchy sequence. The definition of Cauchy sequence are a bit different from the original Cauchy sequence. We can consider that only the second term has a subscript greater than the first term, and then you just define the Cauchy sequence like that. And such a sequence should converge with respect to forward metric. So I mean, we just consider dxix, not dxxi. So, but we can just show that the completeness in this meaning. Yeah, all the faces look like that. Yeah. Yeah. Sorry, yeah. It lies in the face. It lies in the face. So I said that this one is the middle point of these two. So it lies on a. So this one. So you have a face for this one and a face for that one. Okay. So this is something like this. So the spiraling this direction and this spiral to the other direction. So for this is spiral this direction and the spiraling that direction or something. Okay? These two are the extreme points. Here you have something like this. Okay? So this also lies some face, of course, because every point lies on some face. So that their face containing these 3 points. But what I'm saying is that this point is a middle point of these 2 points. And these two are extreme, meaning that it's a kind of vertex. But this point corresponding to that is not a vertex. It's not an extreme. Sorry? Chain recurrent, yeah. So this is chain recurrent. This is chain recurrent, but this is not chain recurrent. So this one is actually linear combination of that one and that one. Actually, we have a. No, I don't think so. I don't think so. I don't think so. For instance, we haven't yet determined the dimension of the face. So we have such a kind of form. So somehow from some information of the mu, you can it should be possible to decide what the dimension it has. But we haven't succeeded it yet. So that's the next problem. So we'd like to know the dimension of the phase. So express in terms of the mu, the chain recurrent geodiscrimination. Good.